eddy currents. Whenever a piece of conductors are placed in changing magnetic flux, say for example you have some piece of metal, okay, this is a piece of metal, and here in the space, say magnetic field is changing, or we can say magnetic flux is changing. Okay, then what will happen? The flux associated with this metal plate changes, and due to that the induced current is produced. Try to understand, for the production of induced current in any metal, the magnetic flux should change. Okay, now the flow pattern is same as swirling eddies, that is fast movement on circular path. Swirling eddies means fast movement on circular path, or we can say the current will move on a circular path as there is swirling eddies in water. Okay, that is fast movement on a circular path in water. Okay, this was discovered by Foucault. Okay, and these currents are called the eddy currents. Okay, now we have one figure here. Okay, a copper plate is allowed to swing like a simple pendulum between the two poles, rather two poles pieces of strong magnet. What will happen here? Okay, this is the north pole of the magnet, south pole of this magnet will be somewhere here. Okay, and here this is the south pole. Okay, so north south poles are there. Now magnetic field is always from north to south, so this is the direction of magnetic field, and this metal plate is supported and it is tied with the thread. Okay, and it is allowed to swing in this magnetic field. Now what will happen? The flux associated with the plate will change continuously as it goes from here from right to left. Okay, flux increases, then it goes out, then again it becomes zero here, then this side it goes, then flux again increases, then again it becomes zero. So flux changes. So what will happen? The electric current, now you see this swirling eddy, this word which we have used, the electric current will move on this circular path in this metal. Okay, now let us say when the metal is going from right to left, the current is on this circular path, that is in a anti-clockwise direction. So when this goes from left to right, the current will be opposite, that is in the clockwise direction. Okay, there are meaning of these arrows and the clockwise anti-clockwise direction. Okay, so it is found that the motion is damped. In a little while the plate comes to a halt in the magnetic field. Now what will happen? This current which is produced here in this magnetic field, this current which is produced in the magnetic field, rather in the plate, okay, this current which is produced in the plate is going to produce the magnetic field which opposes the very cause. Very cause means motion of this plate in this external magnetic field. So what will happen? It opposes the cause, that is motion of the oscillation, or rather we can say movement of this plate in the magnetic field. After some time the plate will come to halt in this magnetic field, or we can say its oscillations are damped oscillation. Its amplitude gradually reduces and it becomes stationary. Okay, after completing some of the oscillations. Now if you think that that is always going to happen, but say for example you remove these magnets, this north and south pole, and just you oscillate this plate, say it takes 15-20 oscillations, rather 20 oscillations to stop if you keep some amplitude from here. Okay, Then you place these two magnets and you observe. Then say it will stop after 12, 13 oscillations. Means its damping is faster when the plate is oscillating in the external magnetic field. Okay. So this way you can understand, we can explain this phenomenon on the basis of electromagnetic induction, why this is happening, why it is becoming damped. What will happen? Magnetic flux associated with the plate keeps on changing as the plate moves in and out of the region between the magnetic poles that I explained. When it is going inside, magnetic flux increases, going out it becomes zero, then again increases. This way what will happen? There will be a change in the flux which induces eddy current in the plate. Okay. Now this direction of eddy currents are opposite when the plate swing into the region between the poles and when it swings out of the region. Okay. If rectangular slots are made in the copper plate, now if you want to just reduce its effect, that of eddy current, then that plate is cut. This way slots are made. So what will happen? The path for the current will be larger. It was earlier the plate was like this, continuous plate. But now it is cut from here and this kind of slots are made. You can see. Okay. Now earlier what was there? The current was having this simple path for the flow. Now that current has to move. Say for example you have this kind of slots. Okay. Now the current which is beginning has to go like this way it goes. Okay. So it has a longer path. Means resistance offered will be larger. More the resistance, less the current. Okay. And current loops are also becoming smaller. Okay. So its effect will be very less, or effect of this eddy current can be minimized. Okay. Thus the phenomenon, or rather pendulum plate with holes or slots, if you make holes or you make this kind of slots here, okay, then the eddy current's effect can be reduced, or electromagnetic damping of the plate can be reduced and the plate can swing more freely and for a longer time. Okay. Note that magnetic moment of the induced current. Try to understand magnetic moment of induced current which oppose the motion. Why the motion is opposed? Because that magnetic moment is produced within the plate and that opposes the motion of the pendulum. Okay, that depends upon the area enclosed by the current. As you know, magnetic moment is given by the formula M is equal to IA. More the area, more the magnetic moment. Now if you find here there is a less area, very tiny slots are there. So area is less, magnetic moment can be reduced and the effect of this eddy current can be minimized. Okay. This fact is helpful in reducing eddy currents in the metallic core of transformers. In transformers which are used in producing electricity, okay, these eddy currents are produced which can be minimized by using this kind of facts of making slots. Okay, electric motors also eddy currents are produced, effect has to be minimized, otherwise it will oppose the motion, and when it opposes the motion the electric motor will not efficiently work and whatever output that we want will not be obtained. Okay, so these are the devices, different devices where eddy currents are produced. It is an inevitable phenomena, but we minimize the effect of the eddy currents. Okay. Eddy currents are undesirable since they heat up the core and dissipate electrical energy in the form of heat. Okay. So eddy currents are minimized by using laminations of metal to make the metal core. Okay. Whenever the metal core is made, its lamination is done, so these laminations are separated by an insulating material like lacquer. Okay, so the effect of this eddy current can be minimized. Okay, eddy currents are used sometimes in some of the places. There are advantages also. First advantage is of magnetic braking in the train. You cannot stop the train by applying mechanical brakes. There is a magnetic braking in the train. Okay, strong electromagnets are situated above the rails in some electrically powered trains. Okay, when the electromagnets are activated, the eddy currents are induced in the rail, which opposes the motion of the train. And what will happen? The brake will be applied, or it will be a smooth braking. So magnetic braking in the train is used for smooth braking. You cannot have a sudden brake when the train is in motion. Then it is used in electromagnetic damping. Certain galvanometers have fixed core which is made of non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the core opposes the motion and bring the coil to rest quickly. Okay, so that is also used in some of the electromagnetic damping. Okay, this use is just you have to remember. Okay, then it is used in induction furnace. Induction furnace can be used to produce high temperature and can be utilized to prepare alloys by melting the constituent metals. When you want to make alloy, the constituent metals has to be melted in a proper proportion. High frequency alternative current is passed through the coil which surrounds the metal to be melted. Okay, because what will happen, the eddy currents which are generated in metal will produce a high temperature. As magnetic field around the metal is changed quickly, the eddy current which will be produced in the metal will produce the heat, changing eddy currents. Because of change in magnetic field, there will be a changing eddy current, and that is going to produce a large amount of heat, and by this heat those metal is getting melted. Okay, it is also used in electric power meter. Okay, the earlier power meters which was using shiny metal disc, okay, that was rotated due to the eddy currents. Now we shall move further about inductance. Okay, an electric current can be induced in coil by changing flux in the coil close to first coil or changing flux in the same coil. Now try to understand, there are two things. First of all, try to understand this way. Say for example, you have this coil and it is connected with a battery and a rheostat. What is the use of rheostat? To vary the electric current. Now when the current is passing, okay, the magnetic field lines are associated with this coil. That is our experience. Now what will happen? This magnetic field is constant. As current is constant, say current I is flowing. Now you are moving this rheostat. And you are changing the current. So what will happen? Either you increase or decrease the current. Say for example, you are increasing the current, then the flux increases. Flux increases means flux changes. What will happen? Induced electromotive force is produced within the coil. Okay, this is nothing but the self-inductance. It is the inductance because the current is changed within the coil, and it is produced by the changing the electric current here with the help of the rheostat within the same coil. The self-inductance it is. Now we take an example of mutual inductance. Okay, now what is in mutual inductance? So both the examples right now I am taking, then it is discussed in detail. Say for example here, This is the first coil. Okay. Now this is the second coil, which is not having anything inside, that is not having the battery. Okay, galvanometer is kept. Okay, now see, the magnetic flux is linked with this first coil. Okay, now by increasing or decreasing the electric current in this first coil, try to understand, you are changing the flux of the first coil by changing the current. Some magnetic field lines are already associated with this because of the current which is passing through the first coil. Now what you are doing, you are increasing or decreasing the current in the first coil. So the flux associated with this second coil will also change. Some field lines are associated, but when you change the current in the first, that is in this, then these field lines associated with second will also change, and that changes the flux, and because of change in flux the galvanometer shows the deflection. Galvanometer shows the deflection. Why? Because the current will be induced, and this is nothing but mutual inductance. Both the things are discussed in detail, but this is a common understanding. Current produced within the coil, by changing the current within that coil itself, then it is self-inductance. And when the current is changed in the second coil and the current is produced in the first coil, or we can say current is changed in the first coil and the current is produced in the second coil because of change in current in the first, then it is a mutual inductance. Okay. Now see, by changing the flux in the same coil, the current can be induced in the coil which is called the self-induction. Okay, the flux through a coil is proportional to current, as you know, that is flux phi B is proportional to current I. More the current, more the flux. If 1 ampere current passes, then whatever is the flux, then 5 ampere current produces 5 times the flux. Okay. Further, if the geometry of the coil does not vary with time, means the coil remains as it is, and if you change the flux, d phi B by dt is found to be directly proportional to di by dt, rate of change of current and rate of change of flux. They are directly proportional. Now there is a proportionality. Okay, more the change in flux, more the current induced, we can say, or more the current is changed. Say it is changed from 1 to 3 ampere, and say it is changed from 1 to 5 ampere. Then in 1 to 5 ampere the induced current produced will be more, because more flux will be changed. If there are n closely wound turns in the coil, then the same magnetic flux is linked with all the turns. Okay, because if there is one turn, then flux is phi B, and if there are n turns, then there will be total flux n phi B, which is also found to be directly proportional to current. And this flux, okay, is known as flux linkage. It is used, which is equal to flux linkage is equal to, or we can say it is proportional to current. More the current, more the flux linkage, we can say. Okay. Now the constant of proportionality we have to place if you want to remove this. If you want to remove this proportionality sign, then we have to place one constant, and this constant of proportionality in this relation is nothing but inductance. So n phi B proportional to I. Now if you write equal to, then some constant we have to place here, and this constant is nothing but the inductance. Okay. How it is defined for self-inductance, that we'll discuss in later case. We shall see that inductance depends only on the geometry of the coil and intrinsic material properties. So the inductance depends on the geometry and the intrinsic material properties. This aspect is akin, means main, to capacitance, which for parallel plate capacitor depends on the plate area and plate separation and the dielectric constant K of the intervening medium. As you know that if you have a capacitance, okay, then capacitance is nothing but C is equal to epsilon 0 A upon D. Now what is A? A is a dimension, that is area of plate. D is distance between two plates. So it is mainly depending upon the geometry of the capacitance, rather the size of plate, distance between the plates and the intervening medium. If there is a vacuum, then we write epsilon 0. And if you place some other material here whose dielectric constant is K, then this new capacitance will be K times the original capacitance. Okay, so whatever medium which is there in between the two plates, on that the capacitance depends. Okay, that part is discussed. And inductance is scalar quantity and it has dimensional formula m1 l2 t minus 2 a minus 2, just you have to remember. Okay, and its unit is Henry. Okay, its unit is Henry. Okay, as such, if you want to find the unit, just then it is Weber per ampere, because flux is having the unit Weber and I is having the unit ampere. That constant which you are keeping here is the inductance. Okay, inductance is Weber per ampere, but in the memory of scientist Henry it is said, or it is taken as Henry. Now self inductance we talk about. Now EMF is induced in a single isolated coil due to change of flux through the coil by varying the current through the same coil. This phenomenon is called self-inductance, that I tried to explain earlier. When you have a single coil and it is joined with a battery and a rheostat, okay, and by varying the current you are changing the flux in this particular coil, then electromotive force is produced as flux changes, and that EMF is produced, that produces the current also. Okay, and this phenomenon is known as self-inductance. Okay, in this case flux linkage through the coil of N turn is proportional to the current through the coil, and it is given by N phi B proportional to I. Proportionality, now see, there is removed, it is a constant L. Okay, where constant of proportionality L is called the self-inductance of the coil, which is nothing but total flux per unit current. If you take L as a subject of formula, then it becomes N phi B upon I. N phi B is the total flux associated with the coil upon current, means flux per unit current. That is, total flux per unit current is defined as self-inductance of the coil. Okay, now we further move. Okay, for it is also called the coefficient of self-inductance of the coil. When the current is varied, the flux linkage with the coil also changes and the EMF is induced in the coil. Okay, so when you are changing the flux, as you know, according to Faraday's law, it is epsilon is equal to minus d by dt of total flux, that is N phi B. Okay, now if you take the differentiation, okay, then epsilon is equal to minus L d I by dt, because we had this N phi B is equal to L I, and if you take the differentiation here, then d by dt, and here also we have to take the differentiation, and that becomes di by dt, as L is constant, and this d by dt of flux according to Faraday's law is nothing but minus E is equal to L di by dt. So E is equal to minus, because minus sign goes on the other side, it becomes minus L di by dt. Okay, thus the self-induced EMF always opposes the change, that is increase or decrease of current in the coil. So whatever self-induced electromotive force is produced, that opposes the very cause, because it is minus sign. Okay, very cause means either increase or decrease in the current in the coil, so it is having a property like inertia. Okay, let us calculate the self-inductance of a long solenoid now. Okay, of a cross-sectional area A is equal to pi r square. That is calculation of the self-inductance of long solenoid. Okay, now solenoid, as you know, it has the area to be pi r square, or you just keep as it is area as A cross-sectional area. Say length is L. Okay, it has n number of turns per unit length, and it is number of turns divided by length. So total number of turns will be equal to n into L. This you can understand easily. Okay. The magnetic field of solenoid, you know, B is equal to mu 0 Ni when I current is flowing. So total flux is nothing but number of turns into flux n phi B will be n into B into A. Flux is B dot A, B A cos theta, cos 0 it will become. Okay. Magnetic field and area vector are in same direction, so theta will be 0. All these things you must understand. Because magnetic field is say in this direction, and area vector of this cross section is also in the same direction. So magnetic field and area both are in same direction. The dot product if you take, then BA cos 0 becomes 1. So total flux n phi B, phi is BA cos 0 multiplied by n number of turns here in the solenoid, so it becomes NBA. Now n phi B, okay, now n is number of turns per unit length multiplied by length. So instead of capital N we write n into L. Magnetic field, see here this total flux n phi B we are finding. Phi B is BA. So n is n into L. B is magnetic field of solenoid, that is mu 0 Ni. So we have written mu 0 Ni into A. So I have just rearranged this mu 0 N square AL into I. So this can be understood easily. Okay. This is again I am trying to explain. Instead of capital N, it is this N into L. B is the magnetic field, that is mu 0 Ni, that of solenoid. A you are keeping as it is. Just rearrange this. So mu 0 N square ALI. Now total flux per unit current n phi B upon I if you take, then it becomes the self-inductance. So n phi B upon I we have to take now in the next step. Okay. See, L is equal to n phi B upon I, total flux per unit current, that will give you mu 0 N square A into L. If we fill the inside of the solenoid is filled with some material of relative permeability mu r. Okay, for example, soft iron is placed which has high value of relative permeability, then this will become L is equal to mu 0 mu r N square A into L. The self-inductance of the coil depends on the geometry and on the permeability of the medium. As we have seen, the capacitance is depending on the dimensions and the material within the two plates of capacitor. Okay. The self-induced EMF is also known as back EMF. Okay, as it opposes any change in the current in the circuit. Its name is given back EMF because this is opposing the very cause, that is change in the current in the coil. Now physically the self-inductance plays the role of inertia. It is the electromagnetic analog to mass in the mechanics. In the in mechanics, mass is the object which is having inertia. Here this L, that is electromagnetic induction, self-inductance L is having the inertia. Okay, it plays the role of inertia. Okay, now obtain the equation of magnetic potential energy or work done in establishing current I. Say for example you want to establish current I in the coil. Okay, now work is required to be done against the back EMF in establishing the current. If you want to establish some current, then back EMF is not allowing to establish that current because it opposes the very cause, that is change in that current. So you have to do some work. This work done is stored in the magnetic potential energy. Okay, for the current I, at an instant in circuit, the rate of work done, that is dW by dt, is power. Power is induced EMF, E into I, V into I, as you know. Now, if we ignore the resistive losses, say for example there is no resistance of the coil, then dW by dt is equal to Li into di by dt. Why? Because we have just now calculated E is equal to, okay, it is L di by dt. Just now we have calculated L di by dt, that is electromotive force, okay, which is produced in this coil, okay, when you are changing the electric current. Okay, just now in that formula earlier we have calculated this. Okay, so here it is E is equal to minus L di by dt, minus sign just we are ignoring, and just now we are taking its magnitude only. Okay, so dW by dt is power, power is voltage into current, and voltage is L di by dt into this I as it is we are keeping. Okay, this I is as it is. Okay, now that dt will be cancelled out from here, and if you want to find total work done, then we have to take the integration. Okay, so to find total work done, it has been taken integration Li di. And integration of I is I square by 2, and if you substitute the limit, then work done will be 1/2 Li square, which is same as the equation is just like a kinetic energy 1/2 mv square. Okay, so here m is playing the role of inertia, or it offers the inertia. Similarly, L here, that is inductance rather, is also offering the inertia. This expression reminds us the equation 1/2 mv square for the mechanical kinetic energy of the particle of mass m, and shows that L is analogous to m, just like m. That is, L is electrical inertia and opposes the growth or decay, or rather increase or decrease of the current in the circuit. Okay, now this part is very easy to understand, and the questions are asked on the basis of self-inductance and this magnetic potential energy. So learn them and write 2-3 times in your notebook. Thank you very much.